All right, welcome back to lecture 6 of electrical systems in agricultural and biosystems engineering. We're going to tackle a problem involving a conventional power plant. We'll try to compute for uh, the, the power available in the plant. This will require some knowledge in thermodynamics because we are going to involve mechanical to uh, electrical conversion or system, okay, that will involve conversion of mechanical to electrical energy. So we have here a problem. Okay, we have a problem involving a gas turbine power plant, and it's known in literature that they have efficiencies ranging from 20 to 35%. Okay, this is the overall conversion efficiency. This will include the mechanical efficiency of the turbine, the alternator, okay, the efficiency of that. So it covers all the operations of the power plant. Now, so we will try to understand what is being required, and let's read out the problem first. So a gas turbine consisting of a compressor, combustor, and an expander has air entering at 15 degrees Celsius. You have the value in Fahrenheit in the enclosed parentheses, and 96.5 kilopascals. That's an absolute, or the equivalent of 14.0 psi. Inlet air is compressed to 385.8 kilopascals absolute, or 56 psi, and the isentropic efficiency of the compressor is 82%. Natural gas is injected to achieve a heating value of 466 kilojoules per kilogram, or that is equivalent to 200 BTU per pound. Assume complete combustion of the fuel. The expander reduces the flow pressure to 102.7 kilopascals absolute, or 14.9 psi, with an engine efficiency of 85%. Simplify the combustion products as having the same thermodynamic properties as air. Cp equals 1.0 and is constant. Taking the isentropic exponent as 1.4, we are asked to find the net work produced by the gas turbine, its thermal efficiency, and the amount of electrical power produced in kilowatts. Okay, so I think we will be requiring drawings for the understanding of the thermal process, okay, the cycle. And let's try to look at what happens in the system. So we have a given, okay. We have an ideal, suppose let's have a chart that will look like this, okay. So it's a heat engine cycle. Now the ideal cycle, let's assume, okay, if you're going to look, it's going to be, you have, it's isentropic, right? So when it's isentropic, okay, take note that you have okay, a compressor with isentropic, okay, that is isentropic, okay, isentropic, okay, so isentropic meaning it goes up to a 0.2, 1, it goes to 3, and goes down to 4. Okay, this is the P, and this is the V. Okay, so it's isobaric. This points 2 to 3. 4 to 1 is also isobaric. Okay, but there's a inefficiency involved, so it's not perfect. So we have a 2 prime. Okay, the compressor is not perfect, so we have an isentropic efficiency involved. So the original is becomes this one. Okay, we have 1, 2, sorry, 3, 4, and back to 1 as our ideal cycle, and we have 1 to 2 as our actual compression, and then you see there's an actual there's a thermal efficiency. So it so happens that we have a okay, we have a 3 prime over here. Okay, so instead of having the original 3, we get a 3 prime, and goes down to 4. Okay, this is 4 prime, a new 4. Okay, it's going to go down there because it's already out of the way. Okay, all right, now we have an expander, and it has its own efficiency. Now we will have to adjust this, okay, to a 4 prime. So that would be our because there's a thermal efficiency involved. Okay, so we have 2 to 3 prime as the actual heat added. And the 3 prime to 4 prime is the ideal. Okay, this is again in the expander. Expansion path. But we have a 4 double prime. Okay, so the ideal work is at ideal temperature is going to be or we have a CP. Okay, but there's an actual CP difference that's going to happen because of the actual heat added. Okay, so let's try to put this in a TS diagram. Okay, temperature versus entropy, and it's going to be something like this. Okay, TS. Okay, again, isentropic, so same S, but it's going to adjust because we have isentropic efficiency involved. Actual heat added, instead of having a 3, we have a 3 prime. So this is 1, 2 prime. Okay. Again, here is we have S equals constant, and here we have S equals constant. Right here, we have P equals constant. Okay. And supposedly the ideal one is it goes down to 4 and goes down back to 1. Okay. Okay, going up, but this is the actual path. Going to the right, up at constant pressure, going down, constant S. This again, P equals constant. In terms of the 3 prime, we have to move it up because of the actual heat added. So this is now 3 prime, and this is the new points. Okay, from 1 to 2 prime to 3, and then to 4 supposedly. But then we have a 3 prime over here, and it's supposed to go down same as, okay. But we have to adjust because of the isentropic efficiency or factor involved. Okay, so okay, going down, it's going to go down this way. All right, we have other constants given, or we have other information given. We have the CP at 1.0 and Q. Okay, this is the heat, right? The heating value of natural gas. So it's 466 kilojoules per kilogram, meaning there's 466 kilojoules for every kilogram of natural gas. It's gas. All right, so the efficiency of the compressor, again, it's how big is the compressor? How efficient? 82%. Okay, and the turbine efficiency is 85. All right, so we're to find the what? Find the work net. Okay. The P, or this is the thermal efficiency, and C, the power available. Okay. What do we do now? We start with the we're going to go through the steps of the process or the operation. So we have to make use of a thermodynamic chart. Okay, and so we start with the T1. Okay, that is 15 degrees, 15.6. Okay, 15.6 degrees Celsius, which is equal to this is equal to 15.6 plus 2. Okay, so we have equal to, you have to find it in Kelvin. Okay, we have T1 equals 15.6 degrees Celsius plus 273. We have 288.6 Kelvin. And P1, okay, we have the entering, P1 is the entering air. Okay, we're using the chart for water. Okay, we're not using the the thermodynamic properties for natural gas. We're using water. Okay, this is a gas turbine. All right, so P2 is the pressure after adiabatic compression. Okay, so P2 is pressure after adiabatic compression. This is in kPa, and this is also in kPa. Now we find P2. P2 is it's not given, it's the air temperature, air temp after adiabatic compression. And since we're taking the absolute P, we want it in Kelvin. Okay. Now T2 is just equal to what? T1 times P2 over P1. You have to raise it to what? K minus 1 over K. And we get what? The pressures are already given. Okay. We have the inlet, okay, at 96.5 kPa, and the outlet is, or the not the out after compression, it becomes 385.8 kPa. Okay, this is equal to 96.5. This is equal to 385.8 kPa, and plugging the values, we get T1 is again 288.6 K times the P2 is 385.8 all over 6.5 kPa. And we have to raise this to what? We have the isentropic efficiency given. The exponent, okay? The exponent is given 1.4. So it's 1.4 minus 1 over 1.4, and we get the T2. Let's try to see how it will. Let's compute for it. 1.4. 0.4 divided by 1.4, 0.28. Okay, so we raise the dividing 25.8 divided by 96.5. We raise this to that value. Okay, times, this is 1.48 something times 288.6. Okay, it's 400. Is this correct? Oh yeah, it's correct. 428.8 Kelvin. Okay, so T2 now is 428.8 Kelvin. After we're actually looking for the thermal efficiency or and work, and we want to get the temperatures. Okay, and because we finally want to have a we want to, or we have, okay, we have to get the value for the W net. Okay, the W net is expressed in what? it's expressed in Cp times delta T, and delta T is measured in the work of the it's actually the net work from the expander and the compressor. So it's expressed in Cp, okay? So W expander minus W compressor. And we get that as the W net. And we have to solve for the Cp or for the Cp delta T for both of these values, okay? So let's try to solve now for the other temperature values. All right, now we want the T2 prime, okay? So there's an actual temperature due to isentropic compression. That's not equal to 428.8. So we have an efficiency involved, right? So the efficiency that is going to identify the loss in temperature. So our efficiency is what? Efficiency is equal to Cp. Okay, since Cp is just one or the same, so we have Cp T2 minus T1 over Cp times the quantity T2 prime minus T1. So Cp just cancels out. We want to find for we want to find T2 prime. Okay, so to get that, okay, we just simply what move this reconfigure this equation. So we get T2 prime equals T2 minus T1 over efficiency of the compressor plus what? Plus the T1. Okay. This is solved for T2. Okay, you can actually check this in the chart, okay, or the but we're not going to use that. Okay, so we have T2 minus T1. Okay, T2 is what? T2 is 428.8 Kelvin minus T1 is 288.6. That's over here. It's over here. 288.6. Okay, over the efficiency, which is what? 0. Yeah, it's over here. 0.82. So 0.82, no unit, and we multiply or we add this to 288.6 Kelvin. We have a T2 prime of let's try to solve 428 minus 288.6 divided by 0.82. Okay, 170 point or 171 plus 288.6. That is going to become 459.6 Kelvin. It's consistent with our chart. Okay, if you see, it moves. Okay, it moves to the right, it moves up over here. So the temperature is consistent with the diagram. Okay, we want to have the T2 prime to T3 prime first before we get to the T4. So T2 prime to T3 prime is the heating, okay, the heating. So it's connected to the combustion. So T2, again, T2 prime is, okay, the addition of heat, right? So we have to use the Q, right? So the Q is involved with the CP. So the change in the temperature is due to the heat addition. So T3 prime minus T2 prime, okay, and you want this value or variable. So we can simply reconfigure this to get T3 prime, and we have Q for CP plus T2 prime. So Q over CP plus T2 prime, and what do we get? We have our Q at 466, right? That is our Q, okay, over here. And we have our CP. So also given, okay, we can simply compute for this one, which is 466 kilojoules per kilogram over the CP, which is 1.0, plus the T2 prime, which is what? Over here. So it's 459.6 Kelvin. Sorry. Divide this one. So we just add, actually, since this is 1.0, but the CP is, okay, it's actually kilojoule per kilogram Kelvin. So you just get, this is actually kilojoule per kilogram Kelvin. So this cancels out. Okay, so the T3 prime is simply 466 Kelvin plus 459.6 Kelvin, and T3 prime is, okay, let's try to solve 466 plus, okay, 925.6. 925.6 Kelvin, and we are now nearing the solution for our the fourth point in the problem. So we get, okay, we actually have a isentropic process again. So let's remember that this is isentropic, okay, from 3 prime, okay, from 3 prime to 4 prime, it's isentropic. So let's have the isentropic process first. It's adiabatic, so T4 prime over T3 prime equals what? It's P4 prime over P3 prime, and okay, it's raised to K minus 1 over K. P4 prime is actually given. Okay. Since what? Since it's going to go back to what? Okay, from 385, okay, 385 to 96.5, okay. So it's going to go back to that value. So there's a change in the pressure. So T4 is what? Well, you just simply move this over to the other side, and you get T4. Sorry, what happened? So T4, we are not at T4. T4 is P4 prime equals P3 prime times P4 prime over P3 prime, the quantity raised to K minus 1 over K. Okay, so this is now just plugging the values. T3 prime is 925.6 Kelvin times the pressure is, it's going to go down, so 96.5 kilopascals over 385.8 kilopascals, and multiply, or we raise this to 1.4 minus 1 over 1.4, and we get the value of 96.5 divided by 285.8 raised to 0.4 divided by 1.4. Okay, 0.4 divided by 1.4, and you want to raise the raise to this one, so it's 0.67. Okay, so it's 925.06. It's 0.67 times 925.6. We get 623, 623 Kelvin. Now we're near to solving the final point, which is T4 global prime. Okay, and that is going to be what? That is going to be an efficiency computation involving the turbine. So with the efficiency of the turbine is Cp times T3 prime minus T4 double prime, T3 prime minus T4 prime. Cancels, okay, Cp cancels. So the turbine efficiency will just be moving over, or remove it, this portion to the side of the efficiency of the turbine, and we can solve for T4 double prime by what? Okay, by subtracting the minus efficiency of the turbine times T3 prime minus T4 double two prime. Okay, so this is what? This is T3 prime is 95.6. Again, the turbine efficiency is 85%. This is 925.6 minus the T4, which we computed a while ago, 623.0 Kelvin. Now we get what do we get here? Okay, T4 double prime is equal to it's lower, right? It's lower. So 925.6 minus 623. Okay, times that with 0.85. Okay, and we subtract this to the 925 we computed a while ago. Okay, so it's 668.4 Kelvin. Okay, so it's consistent. Okay, 666.4. I'm not sure if it's going to show on the screen. 666.4. 668.4. Okay, Kelvin. Now we can now solve for what? The network. Okay, the network is going to be it's going to be the work across the expander minus the work of the compressor, and it's net because you expend work to power the compressor. Okay? So the work of the compressor is Cp times T2 prime minus T1, and we get what? This is just 1, okay, 1.0 times, okay, 459.6 T2 prime, this one, oh sorry, this one, right, minus the T1, which is our original 428, oh no, 288.6, 288.6, this one. Right, so very direct, 459.6 Kelvin minus 288.6 Kelvin, and the work of the compressor is simply 459 minus 288. 288, where's that? Is that here? Why is it not here? 288.6. Oh, 170. Okay. 171. 170. Okay, 171. 171 kilojoules. Assuming we have no mass change. All right, now we have the work of the compressor, expander, sorry, as just Cp times the T3 prime minus the or T4 prime minus the T3 prime. That's going to be that way. T4 prime minus T3 prime minus T4 prime. We move it the other side. Okay, I mean we take the absolute value of that, and that's why we have T3 prime minus T4 prime double prime. So this is 1.0 times T3 prime is 925.6. Okay. Again, this is kilojoule per kilogram, right? Per Kelvin. So that's why we get a value of kilojoules. Okay, T4 is 668.4. So we have it here. Okay, so 668.4 Kelvin, and we simply have it as 257.2 kilojoules, assuming there's no heat loss. So our W net now is 257.2 kilojoules minus 171 kilojoules, and we have this is what? This is 86.1. Sure, I'm very poor with 257 minus 0.2. minus 171. Yeah, to 86.2. Okay. Kilojoules. Now, this is our final answer for the net, and we can easily solve for the efficiency the thermal efficiency, which is just the W net over the Q. Okay. We have the Q given by 466, right? 466 kilojoules per kilogram. So this is per kilogram. Okay, so 86.2 kilojoules per kilogram divided by 466 point. Oh no, it's a whole number. So we get 86.2 kilojoules per kilogram, or 466 kilojoules per kilogram, and get what? $18.5. Okay, it's 18.5%, way below the range for gas turbines. We'll have to improve this efficiency still. Okay, now this is the efficiency. It's way below that of the in literature. So we now solve for the available power. P is simply what? It's 85. It's 86.2. Okay, kilojoules for every kilogram of your natural gas. Okay, so how much you spend will depend on the capacity, but okay, we can compute for the available power, and we have this as, okay, we just have to convert this to watt hours. Okay, and we're being asked in watts. So when we have the operations, the hours of operations, we can just simply, for example, multiply it with the, for example, 1 day is 24 hours. Okay, so we have 86.2 kilojoules times 1 over 3,600. So we get okay, 23.8 watt hours. And if you want to again to get the per day, okay, so it's 24 hours per day. So we have 23.8. Okay, so it's going to be 571.2 watts per day. Well, again, it's on a per kilogram, okay, per kilogram per day. You have to multiply it with the amount, okay, of input, okay, of input natural gas, okay. But assuming we have a complete combustion, okay, there's no involved efficiency in combustion, because there's another factor there. So if for every kilogram, okay, of a natural gas, okay, we'll be able to produce this one. So if the input would be 1 kilogram, then it's going to be this amount of value. All right, so that would be all for the discussion on the solution for a conventional power plant. Now, the electrical efficiency of the alternator is still not well. We have to have an efficiency involved in the alternator. Still, if you're going to have an actual operation for this one. So given that this is the available power, okay, and converted by the alternator completely 100%. So this is what can be transmitted or delivered to the grid. Okay, this 571.2 watt or 23.8 watt hours. Okay, this is in actually it's in joules. Okay, but okay, it's simpler to solve for the watts if we have now the unit or the value of hours, which we can easily multiply by the hours of operation of the plant. All right, so next meeting, we will be discussing the non-conventional, so the renewables this time. I'll see you until then.